Ladies and gentlemen. Ladies and gentlemen, your class recording for today has started, so you can be whoever you want to be for the next 43 minutes.
Hello, Governor.
We classed up the morning announcements this morning, too, with a little British accent as well. All right. So today, our plan for today. First, we need to finish up the outline from yesterday on our introduction to what waves are and stuff like that. And then wanted to get started on the outline they gave you today, which deals with the properties of waves. We won't get through the whole thing. It's okay, I didn't plan to get through the whole thing, so that's where we're going to end up. But yesterday, we started in on introduction to waves, and there were two main objectives for yesterday. Here were the two main objectives for yesterday. So, to start off class today, I would like you to take 30 seconds, well, maybe a minute, because I want you to do both of them. Take a minute and discuss these two objectives with the people next to you. I know we did this in class yesterday, but just to refresh our memory where we were and stuff like that. Take a minute, discuss these two objectives, then we'll come back together and discuss as a group. Ready? Go.
Mechanical waves need a medium. I know the transverse waves, electromagnetic waves, don't both mechanical waves. Transverse waves is both perpendicular, and transverse waves, they both have to use a wave. Oh yeah. And they both transverse. Yeah, they do. What does it mean by perpendicular and parallel? Crap, I forgot to say that. So let's see it say that there's rows that made that and it's being like wave, like you know how you wave it up and down. And it like the bump goes up. The rope is facing this way, but the bump goes transverse wave is mechanical wave, so that's what we like side to side.
Okay, let's discuss. So first objective says compare and contrast mechanical waves and electromagnetic waves. Let's do the comparison part first. What makes mechanical waves and electromagnetic waves similar to one another? They both carry energy, right? They both are responsible for taking energy from one place to another, so that makes them similar. How about different? What's the one big difference between them? Catherine, go ahead.
Mechanical waves need a medium and electromagnetic waves don't.
Mechanical waves need a medium, electromagnetic waves don't. What's a medium, Catherine?
It's something that the energy passes.
That something has to be what? Matter, right? It's matter that the energy passes through, and that's the wave, okay? All right, the second objective, compare and contrast transverse waves and longitudinal waves. Let's do the comparison first. What makes transverse waves and longitudinal waves similar to one another? Sure, go ahead.
They're both mechanical.
They're both mechanical waves, meaning that they
Both require a medium.
both require a medium to travel through. What makes them different? How are they different from one another? Sure, go ahead.
In transverse, the particles vibrate perpendicular, while longitudinal, the particles vibrate.
So in transverse waves, particles vibrate perpendicular, whereas longitudinal waves, particles vibrate parallel. So let's discuss that a little bit more. All right. Nope. Okay. So transverse wave. As we've established already, this is the back of your outline from yesterday, so if you didn't get it all filled in on your own, you want to fill it in now and go there. Okay. So, transverse wave. First, like the definition says, the wave causes the medium to vibrate at right angles to the motion of the wave. And it's Roman numeral number 3, letter A would be a transverse wave. If I said at the beginning of class yesterday, when we first started this, said, hey, draw me a wave, most of you would probably draw a transverse wave, because most of you would probably draw a picture that looks something like this. So there's a girl, she has a jump rope, maybe she's at the playground, whatever it is, and she takes and she makes a disturbance in that rope, right? Her hand creates a disturbance. Kevin, go ahead.
What goes for A and B?
A is, above?
Yeah.
Okay, so for mechanical waves, waves need a medium to travel through, right? And then the material that the wave is, that carries the wave is called the medium.
Oh.
Okay, yeah, so. And we said, Captain, like you said, the medium has to be what? Matter, in order for it to be a mechanical wave. All right. So here, girl at the playground, she has a jump rope, maybe somebody's holding it at the other end. And then she creates a disturbance in that jump rope. Go, Jay.
I was just wondering, what's the letter D on the back front page?
Energy.
Because that's what waves do, right? All right, I'll do it in the front side. All right, so now, the transverse wave. Transverse wave, like the definition says, wave causes the medium to vibrate right angles. Here, girl holding a jump rope, she creates a disturbance in that jump rope by moving her hand. That disturbance, the energy of that disturbance is then carried along the jump rope in the form of a wave. In this case here, she makes repeated disturbances, right? She keeps shaking her hand up and down, up and down, up and down, up and down. But in this case here, the waves are traveling in this direction, right? They're going from her to her friend on the other end that's holding the jump rope. But as that wave is traveling along the jump rope itself moves up and down, up and down, up and down. So the wave is traveling this way as the rope is going up, down, up, down, up, down. That makes it a transverse wave, perpendicular to the way that the wave moves. The one on the right-hand side is also a transverse wave. As that object is moving from front to back, right, or from one girl to the other girl, the rope is going side to side, side to side, side to side. That's a right angle as well. It's not the same right angle, but it is a right angle. So both of those would be considered transverse waves. As far as identifying parts of a transverse wave, this is going to be important to help us understand some things a little bit later on today. But we named certain parts of this transverse wave. For example, the crest. The crest is the highest point of the wave from the rest position. So the rest position, sorry, I'll do this here. So in this picture here, we have two crests. The rest position being where would the jump rope be before any disturbance was created in it. That's represented by that black dotted line or dashed line. That's where the jump rope would be before any disturbance was created or before any wave was traveling through it. The crest is the highest point. And then on the other side, you have the trough. The trough is the lowest point. Two troughs in that picture. So when we talk about describing a transverse wave and how we measure parts of a transverse wave, it's important for us to know where the crests are, where the troughs are. That will help us to do some measurements that we'll talk about here in a little bit. All right, good with transverse wave. The other type of wave that we talked about that we introduced in the flow chart yesterday is called a longitudinal or a compression wave. And like its definition says, right, a wave where the vibration of the medium is parallel to the direction of wave movement. Longitudinal wave or a compression wave, those terms are interchangeable. They mean the same thing. And really good example of that would be something like this, where you have a slinky. And you take the slinky, and instead of shaking it up and down, you sort of push it and pull it, and push it and pull it, and push it and pull it, right? When that happens, we'll find areas of the spring that are different from one another. There are certain areas of the spring where the coils are mashed together. right, where the medium has been drawn closer together, or the density of the medium has increased. We refer to those areas as areas of compression. In that picture of the slinky that you have in your notes, there are two areas of compression. Two areas where the coils of the spring are closer together and the density has increased. On the other hand, if there are certain areas where the density of that material has increased because of you pushing, when you pull it back, you create areas where the density is decreased. We refer to those areas as areas of rarefaction. Two areas of rarefaction here. So we're either increasing the density of the medium or decreasing the density of the medium. Squishing it close together or spreading it far apart, right? In these descriptions, right, it says area where the particles of the medium are close together. That would be areas of high density, right? In the rarefaction areas where particles of the medium are spread apart, that would be areas of low density. So high density, low density, high density, low density, high density, low density. The slinky is something we could probably all at least sort of picture in our mind, right? Push, pull, push, pull, push, pull. Maybe not the most practical example, but something that we could probably picture. As far as practical example goes, okay, if you think about someday in the near future, hopefully, we'll actually be able to open the windows, you know, at your house, in this classroom, whatever it is, okay? And you have that experience where by closing the door on one side of the room or opening the door on the other side, on one side of the room, you can get the curtains to move on the other side, right? Are we okay with that experience?
Wait,
Yes?
what?
So Maura, have you ever, like, when you open the door to your room, like if you walk into your room, if the window's open, the curtains sort of get like pushed against the screen,
Oh, yeah.
right? That opening of that door, right, when you open it into your room, you create an area of high density. All the air that was behind that door, you sort of squish together. You know what I'm saying? That's the disturbance that causes the wave. That energy is then transferred through the air in the room and eventually hits those curtains and moves them. Okay? But we can also go the other way around. If the door closes, sometimes you'll see your curtains sort of like fly away from the window. Does that sound familiar? Get that? In that case, just the other direction. You've created a rarefaction, an area of low density, because you moved the door and there wasn't any air behind that door. Sorry, there wasn't any air is sort of a strong terminology. There's less air now because of that moving of the door. It creates an area of low density. The other parts of the room go to fill it up, but that causes the curtains to then move. So we can move those curtains across the room without actually having to go over there and push them. Not that that does anything really for you, but you know, it happens at least. The most practical type of longitudinal wave or compression wave are sound waves. Sound waves are all longitudinal/compression waves. Whether they are sound waves created by a human voice, vocal cords moving back and forth, or whether they're sound waves created by a speaker, where if you've ever watched a speaker, like a slow motion version of a speaker before, there's a little part of the speaker that moves back and forth, back and forth, back and forth. And as it moves, it pushes air and it pulls air, pushes, pulls, and that creates those compression waves. Or if it's created by a musical instrument, either a string that vibrates through the air like on a guitar or a piano, or whether it's like on a clarinet or a saxophone, the reed that moves up and down as you blow into it, those are all compression waves, longitudinal waves, areas where the air is high density and low density. Good there? All right, to wrap this one up, let's go here, electromagnetic waves. Okay, so electromagnetic waves are transverse. So when you draw electromagnetic waves, we draw them as transverse waves, but they're not mechanical. Okay, They have the same shape, but they don't require a medium. Instead of the medium moving at right angles, we find that there are changing electric fields and magnetic fields. We introduced the ideas of electric fields and magnetic fields earlier in this class when we talked about electricity and magnetism and the things that affect it. Remember, it's charges. A lot of times it's electrons, but it could be protons that move. And as those electrons and protons move, they cause a change in the area around them, right? That's the electric field. And remember, we talked about that when charges move, they can cause magnetism, that idea of electromagnets. Electromagnetic waves do not need a medium to travel, right? They will travel through a vacuum, travel through an area where there is no medium, there is no matter. And just like a mechanical wave needs a disturbance to be created, so does an electromagnetic wave. It's just that that disturbance is generally the movement of an electron or several electrons. As those electrons move, that's the disturbance that causes the wave. All right, good there. Jude, good.
How can electromagnetic fields change if there's a magnet?
Okay, because the electromagnetic field, or the electric field, or the magnetic field, remember we said it's just an area that sort of surrounds the magnet where it can affect other things. Does that make sense? Does that sound familiar? That, remember we talked about if we have a bar magnet, let me go here and draw. Alright, so here, so there's our rectangle, and we'll label this end north, and we'll label this end south, right? And we said that there were lines that flow out of the south pole and go to the north pole and look like this. Yeah, does that sound, that sort of sound familiar? June, that area around the magnet exists whether there is matter in that space or whether there isn't matter in that space. A magnet would work out in space just the same as it works here on Earth because the field is there even if there isn't any matter there. So what happens is, and June, we'll talk about these more a little in more detail after next week, after your quiz next week. But there's actually two waves that sort of slink through one another. It almost looks like two snakes that sort of like they curve out and they come back together, and they curve out and they come back together because one affects the other one. And so they sort of, instead of traveling through a medium, they almost like travel through each other. And that's why they don't need anything else to travel through, because they have the electric field has the magnetic field, and the magnetic field has the electric field. Is that okay, at least for short description? Kind of. It's a pretty complex process. Basically, we just want to introduce it to you at this point in time. So if it doesn't completely understand it, don't worry quite so much about it right now. We'll talk about it more in detail next week. So, all right, good. Okay. So let's start off and go here. What we want to do now in the other outline that I gave you, wait for a second there. The other outline that I gave you is start talking about how do we classify, no, sorry, not classify, how do we describe these waves? How do we distinguish one mechanical wave from another mechanical wave? And that starts with me doing this. Okay. So, take the pendulum, back and forth, back and forth, back and forth. Our discussion about the properties of mechanical waves starts with periodic motion. If we describe something as a periodic motion, what does that mean? If we describe something as periodic, very good.
I think it deals with time.
Deals with time, and specifically what about the time, Trey?
Like it's consistent.
It's consistent, right? Something that is periodic repeats at a nice regular time interval. Okay? This pendulum that I have started up here is repeating at a nice regular time interval. It goes back and forth, back and forth, and back and forth. And it always takes the same amount of time to do it. What are some other things that you can think of that repeat at regular time intervals? Catherine, go ahead. Hands on a clock, right? The movement of the hands on a clock repeat at regular time intervals. What else? Maybe something on a little bit bigger scale. Yeah. The Earth rotates around, the Earth rotates around its axis, but then it also does what? As it's rotating around its axis, it's also rotates around the sun, right? Revolves around the sun. We should say revolves, actually.
Sorry.
Those are all regular periodic motions, right? Now, the reason why that's important is because we talked about that waves are created by a disturbance. But more often than not, it isn't just a single disturbance that creates a single wave. A lot of times it's a repeating pattern of disturbances that causes a repeating pattern of waves. There are some instances where you have like an isolated disturbance that creates one wave, like a tsunami, right? An earthquake, the disturbance, creates a disturbance on the ocean floor. The ocean floor, the energy of that disturbance is carried through the water, and you end up with a tsunami, right? But a lot of times, it's the disturbance that creates the wave is at a nice repeating interval. So a lot of the terms we use to describe this are also the terms we use to describe the waves that are created by these repeating intervals. So the first term that shows up is the period. And we use the capital letter T to represent the period. If we use T to represent period, that means that it might relate to what? Time, okay? And that's what it is. So period is the time required for one full cycle. Notice, one full cycle is underlined. Okay? It's the time that it takes for an object to return to its starting position. That can be a little misleading from a pendulum standpoint. It's easy if you start it from one end. So if we talk about like this pendulum and we time it from here to here, right? If it starts all the way here, it goes back and then it comes forward again. That's one full cycle. It can be a little misleading if we start our timing in the middle, right? Because it keeps passing through the middle, but every time it passes through the middle, that doesn't mean it's one full cycle, right? Every time it passes through the middle is only half of a cycle, right? If it goes from middle to middle, it hasn't done a full swing. So you have to kind of keep that in mind when you're looking at pendulums and waves, that when we talk about the period, one full cycle, okay? Good there. All right, that idea then leads us to the next thing that we use to describe periodic motion, which we also use to describe waves, and that is the frequency. Frequency is the lowercase letter f that we use to represent frequency. So like its name suggests, what is the frequency going to tell us? Because you know something about English, you probably figure it out. John, go ahead. Right, or how often, right? Or in this case here, we talk about how many. So the number of cycles that occur in 1 second. Period is a time measurement. Frequency is a counting measurement. How many cycles occur in 1 second? Okay? Here, this pendulum doesn't complete a full cycle in 1 second, right? So its frequency would be less than 1, because it doesn't complete a full cycle every second. If I had a pendulum that could go back and forth in 1 second, right? Start here, go there, and come back to where it started in 1 second, it would have a frequency of 1. The unit that we use to measure frequency is the hertz. H, capital H, lowercase z. When you see capital H, lowercase z, that represents cycles per second. So if we have a motion that has a frequency of 10 hertz, that means 10 of those things are happening every second. If it's 1,000 hertz, 1,000 of those things are happening every second. Okay? If you know anything about music theory and stuff like that, if you ever like see a tuning fork, you ever see a tuning fork? Does anybody know what a tuning fork is? Tuning fork is it's a little like metal thing, and you hit it and it creates a tone that is supposed to represent that musical note, either A or C or G or whatever. And if you look at those tuning forks, or if you have like a digital, you can get like a digital thing too that creates those tones, right? All of those notes are associated with a number. Okay? 440, 560. These are associated. Those musical notes are associated with a number. That number represents the frequency of that vibration. So 440. Do you know what note 440 is? What is it? Oh, you shook your head.
I know what it means, but I just don't know how it sounds like my heart.
No. What note is it?
Oh, 440. That should be an A.
I think it's an A. Yeah. So 440 hertz is what our ear interprets as the musical note A. But that means that in order to create an A on the piano or on some other instrument, the vibration has to occur 440 times every second. So if you're on the piano and you hit the note that says A, right, if you hit the key that corresponds to A, then that string inside the piano vibrates back and forth 440 times every second. And that's how the frequency works. Okay? Good there. All right. To illustrate the next point, I'm going to add another pendulum. Okay. Ready? Here we go. It's kind of freaky, isn't it? All right, so discussion with the person next to you, in front of you, behind you. How do the period of these two pendulums compare to one another? How does the frequency of those two pendulums compare to one another? Discuss. Go.
Okay, well, this one for you, the small one, so it looks like it has like cycles. And then time required for this has it takes less time for one cycle. So I guess it has oh yeah, that's what it is. The shorter amount of time it takes to
Wherever, yeah. Kate, Rachel, and I all are missing because of the National Spanish Exam. Yeah, we're missing. Yeah, so it's
I tried to
Okay.
Spanish state spelling class.
Let's discuss. So, which of these pendulums, top or bottom, has the greater frequency?
The top.
Good. Top one has greater frequency, right? It moves back and forth more often than the bottom one does. Which one of those pendulums, top or bottom, has the greater period? The lower one. It takes a longer time. What kind of relationship do frequency and period have?
Inverse.
They have an inverse relationship. Okay? So, we can relate the frequency to the period through an inverse relationship. Mathematically, what does an inverse relationship look like?
It's like perpendicular lines, basically.
That's what it looks like on a graph. If we look at it like in an equation, what does it look like?
Oh, it would be like
No, that's like on a graph.
So like
Y equals
K.
negative x.
Ah, y equals not negative x.
Positive Q. Negative one.
Square root of x.
Y equals
X squared.
x to the negative 1.
Wait, when am
So, mathematically, it would look like this. F equals 1 over t. Okay? Because if the period gets bigger, right, where is period in this fraction? The denominator. If the period gets longer, if it takes longer, what happens to the frequency? It gets smaller, right? If it takes longer to do one cycle, you're going to do less cycles per second. Or the other way around. T is equal to 1 over f. Right? If the frequency increases, if there's more cycles every second, the amount of time it takes for one cycle decreases. Inverse relationship between frequency and period. Okay? Good there? All right, next. Oh. One important thing to keep in mind, we'll look at this in lab. The frequency of the wave that is created depends on the source that creates that disturbance. Now, the pendulum's a little different because gravity is causing that disturbance over and over and over again. But if we go back to the girl who was shaking the jump rope at the playground that we looked at earlier, right? The number of waves that are going to be created in that jump rope depends on what? We go back to that girl who was on the playground before. If the number of waves in that jump rope depends on what?
Work.
Oh, yes, but where does that work come from, Trey? Yes. How does force from who? From the girl, right? If we want to make more waves in that string, what does the girl have to do? Shake. Well, maybe not more force, more shakes, right? So the number of shakes that she does is equal to, that's her frequency, and that equals the frequency of the waves. So the frequency of the waves depends on the frequency of the source causing the waves. Easy, man. We've still got 5 minutes left. All right, next.
Is that an upside down Y?
It looks like an upside down Y. Actually, it is a Greek letter. That is the Greek letter lambda. Okay?
Lambda.
So it's actually a lowercase lambda. All right.
What is that?
Uppercase lambda is just like an upside down V. That's uppercase lambda. So, but anyway, so next thing, wavelength. Because of its name would suggest that wavelength is telling us about what? A distance, right? So it's the distance between the same point on two waves that are next to each other. This one really doesn't apply so much to the pendulum. It's kind of hard to talk about the wavelength of the pendulum. But if we get if we get waves drawn on a paper, or if we look at a picture of waves, we can talk about, okay, how long is it from crest to crest? Or how long is it from trough to trough? The same point on two consecutive waves. Once again, wavelength and frequency are related to one another. If you look at the pictures down at the bottom of the page, right, they illustrate that relationship for us. So here, right, in this case, frequency has increased, right? If this picture represents 1 second, this is 1 hertz, because one wave every second. Here's 2. But what has happened to the length of those waves? They're shorter, right? So as the frequency increases, the wavelength decreases. What kind of relationship? Inverse relationship, right? So increasing the frequency will decrease the wavelength. They have an inverse relationship. So F equals 1 over lambda, or lambda equals 1 over F. Those are just mathematically representing that inverse relationship. Catherine, go ahead.
I'm kind of confused. How do you get the 1
that, okay,
1 second.
the one is just how we illustrate the idea that one increases while the other decreases. Okay? So hold on a second. Anyway, Reese, let me at least finish this description. So Catherine, with this, right? If we make the bottom of a fraction bigger, what has to happen to the answer of that fraction? It gets smaller, right? So that's how we illustrate the inverse nature of their relationship, right? That one gets bigger, the other one gets smaller. Mathematically, that's how we do it, right? Here, it's easy to see from the picture that as frequency increases, wavelength decreases, but mathematically we show that with the fraction.